this is his idea. You have light coming in, right, and it sort of diffracts, and it comes through the double slit and diffracts, and you get some kind of interference pattern, right? But what do we just say? We just said that light doesn't travel in waves. Well, if light doesn't travel in waves, that doesn't work. And I'll sort of jump down to here. Thomas Young based his drawing on fluid mechanics, right? If you go back and you look at the original diagram that Thomas Young made about light and the double slit experiment, there's no way he could possibly see, you know, the individual light waves. I mean, we can't do it today. Humans can't do it. So he just made the diagram based on what? What he knew about fluid mechanics, and he used water. That's where it came from. But in truth, going back up to here with no waves, we still have the photons, right, from the different 7 different colors. And so when, you know, light goes through here, what it's going to come out basically a similar, you know, instead of waves in a wavefront, which doesn't exist, it just comes out as tiny, the photons. They make a similar pattern that looks like an interference pattern, but it's not. It's a probability density. In other words, this is an interference pattern. If you think about it, Newton had sort of the corpuscular idea about it, right? Just little bops of photons. So if you shoot photons here, it will bounce off and move and do whatever, and depending on how you have it set up, it will give you this pattern or slightly different patterns, right? It has nothing to do with interference. They don't interfere because why? They're individual photons and they can't interfere with each other. Think about water and waves, right? And then think about maybe like a beach ball. You know, how a beach ball travels versus how a wave travels is a major difference. Same thing here. You have those little balls. All you're seeing here are what? Probability densities, right? Visible light does not travel in waves, right? If it travels in singular photons, right? The display is a probability densities, not interference patterns. So that's what I want you to get out of this. This is just another support for the idea of why light does not travel in waves. It doesn't travel in waves. The photon, I mean, the other idea that I've seen with particles and things, that sometimes if you shoot an electron or some small object, that it actually goes in and comes back out and goes back in again to interfere with itself. No, this is science, and it's based on reality, you know, not speculation, and that doesn't happen. You know, particles, whether they're photons or electrons or anything, you know, do not interfere with themselves, right? They don't. They go in and they behave just as a regular ball, let's say a ball or something would. So this applies to the particles. Photons, particles do not interfere with themselves, and the other is just the Thomas Young that we talked about. And that's why it's been here, because Thomas Young made him I think he was doing the best he could, but he made a mistake in using water to mimic how light is propagated, and it was completely wrong. So light, I mean, unless it's something very special that people are trying to do, you know, other things being equal, just follows in a straight line, and when it hits and moves and you'll get the same kind of look. Go look in any textbook and just realize it's not waves interfering, it's just particles, you know, that are moving and being reflected and hitting or whatever, and that's what you end up with. You end up with a probability density, not a interference pattern. So I think we kind of bashed that one down, right? So the wave, this idea of the wave-particle duality is what? Is wrong. There is no wave-particle duality to light. There's just light. Photons moving in a straight line unless otherwise hitting something, or in a field like bending, right? It bends in Newtonian gravity. It bends in Einstein's general theory. So, I mean, light can bend. You can still use this, which is particles, has nothing to do with waves, right? So that's the other part. It just takes this goes back to this as a reason why waves, photons don't travel in waves, because Thomas Young was wrong. It's completely wrong. So let's go ahead and I'll set up a new screen. If this stays up. So, here again we have a screen. There's a couple ideas that I just wanted to mention here. Here we have, let's say there's a galaxy, right? And it's in motion. It's in motion to the right. There's an observer over here, right? So that is redshifted. Well, let's say if it's moving, it's moving away from somebody at that point, right? So it's redshifted. These are not, again, not a wave, they're spaces. Somehow you have to account for that. You can call it distance, space, whatever. You get the idea. So c, which is fixed, the speed of light in a vacuum, the space times the frequency. So we still have the frequency, we just replaced lambda with s, or I did for the time being. What happens, if the observer is over here, then there'll be a change in the space, right? And there'll be a change in the frequency. The space will get larger, the frequency will get smaller, right? That's basically all what we're doing now. If you look at a redshift, the speed of light is still the speed of light, even if it's going away from you, right? But what happens is, as the motion of the object goes faster, the photons that are coming out at greater distances, which is what accounts for the change in the space and frequency being lower. What's the other over here, right? So now it's coming toward you, right? Again, no waveform. You have the speed of light. So now the object is coming toward you. You have the speed of light, the space, the frequency, still there, but you have the speed of light. Epsilon is the motion of the source, which is the galaxy here, equals the speed of light, right? Equals the space times what? The frequency, which increases, right? So the change in the frequency goes up. And I'll explain it in a second. But, so space, the frequency increases, but what we're thinking now, what the thinking is now, is that blue light or shifted light coming towards us, the waveform, which does not exist, contracts. That's not correct. That's not what's happening. You add the motion, you add the speed of light with the motion of its source to get the space remains the same, and then the frequency increases. Well, why is that? Well, think about this. If you're on an embankment, right, and there's a pickup truck, and on the back of the pickup truck it has a little gun that shoots out golf balls or ping pong balls or something, right? I mean, if it's standing there, you're just going to get the usual spacing plus a given frequency, right? That it comes out, like 1 every 5 seconds or something. If it starts to take motion, right, then what's going to happen? I mean, the spacing between them is staying the same, but the frequency goes up because of the motion of the truck, right? The motion of the truck E is added to it, and you end up with a higher frequency, which is this, which might not be the best way to say it, but it is, but it can be. right? So the frequency will actually go up, not because the photons are compressed more. It's just because the speed of light is added to the balls, going past, and it'll lift up anyone on the bank will look up and see a higher frequency, right? Because of the motion of the truck. Same thing here. That's the motion of the truck. Right? You add the motion of the source to the speed of light, and you come up with a blue shifted in a higher speed of light. So that just, if you go back and you look at one of my earlier videos, it was breaking the light barrier, adding velocities beyond the speed of light, and that's what you're doing. I guess I'm looking at this and say C equals F, so C plus E, right, epsilon, and change there. All right, no waveform motion. I think I killed that one. So, I mean, that's one other thing, right? The blue light that you think is happening because of a change in the wavelength, well, that's impossible because there is no wavelength to change, right? It's just the motion of the source with the speed of light from that source that equals that you can break the higher speed of light from. That's all. One other thing I wanted to talk about, just so you understand, is the idea of polarization, like polarization in glasses, sunglasses. And I mean, to look at it, I have something over here, and it just has two aspects to it. Say you're looking down on something, like our track example, and this is a wall of posts or something like that. Somebody's back here, shooting little marbles or something, whatever they might be, and one travels in a wave and the other travels in a straight line. Well, contrary to what you might think, the difference between the ones that travel in a wavelength and the ones that travel in a straight line, the difference will be statistically zero. Because sometimes when they travel in a straight line they'll go through, sometimes they'll travel in a straight line and not, and even with a wavelength where the white or the straight line might be stopped, a wave, that's moving up and down in a wave, would go through. So if you put a number of points, one was traveling in a wave and one straight line, there wouldn't be any real difference. There's no statistical difference to that. Polarization has nothing to do, when they have polarized lenses and whatnot, has nothing to do with the wave of light. There is no wave to light, so that can't be true. It's just straight lines. Now, a lot of what they do with polarization is really what? What kind of light is it? It's reflected light. Glare, right? That's reflected light. And that's basically what they stop. And so it matters how many of the